Welcome everyone to section number 8. This is Newton's method and yet another application of differentiation. So in this video we're going to go ahead and introduce and kind of give you a bit of an explanation behind what is this thing's Newton's method. And the claim is that this is going to be an algorithm, right? This is going to be an algorithm that can help us solve fairly complicated equations. So let me give you an example to kind of help us understand what Newton's method is going to be doing. So I would like to go ahead and solve x to the fifth plus x minus 1 is equal to 0. And if you'd like to, you can go ahead and pause the video and try to solve this one. I'll give you guys, 10, 20 seconds, or pause it for as long as you want. Try to solve this equation. All right, the claim is that this is a very tough equation to solve, that we don't actually have the techniques down. Algebra didn't really go this far. We're really good at quadratics. We can do some cubics and quartics if they factor nicely and stuff like this. But actually, this one is a very difficult equation to solve. So in fact, I've already pulled up here on, this is an extension of Mathematica. And I wanted to solve this x to the fifth plus x minus 1. And you can see that there's a solution here between a half and 1, so maybe around like 0.7 or 0.8 sort of deal. But if you go down, right, it'll actually tell you what the exact answer is. So here is the exact answer. So if you got this, good job, right? So you got it exactly correct. But this is a very difficult thing to solve. And that's what Newton's method will be helping us with. So the idea behind Newton's method is that instead of actually being able to solve these things, maybe if we can just get an approximation for the solution, that will be good enough. Maybe if we can get a decimal approximation with maybe 100 digits accuracy, or 1,000 digits of accuracy, that will be good enough, and it doesn't really matter what the exact answer is. Okay, so let's go ahead and play around with this thing a little bit. So I went ahead and I graphed this in our Desmos calculator here. Let me go ahead and bring that up. And I'm going to describe to you the ideas behind Newton's method. All right, so here is our beautiful graph. X to the fifth plus x minus 1. Again, you can see that it crosses the 0. It's equal to 0, somewhere between maybe a half and 1. And the idea behind Newton's method is that we're going to use tangent lines, and tangent lines will help us approximate this solution here. So let me go ahead and I can go ahead and click this over here, and I'm going to generate the first tangent line. I'm just going to take a guess. So I'm going to say at 1, I'm going to draw the tangent line, right? 1 is fairly close to where our solution is. And we can see that the tangent line, where it crosses, right? So it crosses down here, and actually I have the second point. So it crosses right here. I can zoom way in, or I can actually just click here and it says 0.833. So this is where the tangent line is equal to 0, where it crosses the x-axis. And so maybe this is a good second guess. And so then I can play this game again, right? So I could ask, well, what is the tangent line at this point? So instead at 1, at this 0.833, and I can draw the tangent line at this point. So now we have this one. And you can see this tangent line crosses the x-axis, and it's getting even closer, right? And so you can zoom in maybe and see that this solution, all right, 0.7644. That would be my third guess, right? My first guess, my second guess, my third guess. This is getting closer and closer to this where the function itself actually crosses the x-axis. And so let's go ahead and I can bring up this third point, right? So this third point, I go ahead and I map it on the actual function itself, and then I can draw its tangent line. And you can do this kind of as many times as you want. You can do it, make a computer program, you can do it 100 times, 1,000 times sort of deal. But you can see now that this red line gets very, very close indeed. Still not quite equal, but you can see that if you zoom in more and more and more, that it is very, very close. So if I go ahead and click here, this is 0.755. And actually, if I click over here, it should tell me the actual 0.7549. So very, very close indeed. So by using the tangent lines, in this case you can see only 3 tangent lines is what it took, we can get a fairly accurate estimate for where the function itself crosses the x-axis. Or another way to say that is when the function is equal to 0. All right, so I think this is a great way to visualize and represent what Newton's method will be doing, but let's go ahead and bring it back to our notes and let's try to write some stuff down to help us remember this later on. All right, so here is the idea behind Newton's method. Let's go ahead and I'm going to draw some pictures as we kind of talk through these things. And I'm going to go ahead and maybe draw a nice function here. So something like this. This is going to be my f of x. And remember, Newton's method is used to help find zeros or solutions or where these things cross the x-axis. Sometimes these are called roots of the function. Okay, the first step is to take some initial guess, right? I'm going to call this x1, and even you can have this be a fairly bad guess. So maybe over here, right, I'm going to go ahead and guess that this value right here is my x1, my first guess. The next step that we want to do is find the tangent line. So I'm going to go ahead and just sketch the tangent line here. There we are. And the claim is, well, it's a line, right? So we can figure out where it crosses the x-axis. That is where it has height 0 or y equals 0. And wherever it crosses that x-axis, this becomes our second guess, right? And notice that this is now getting closer to this actual 0 over here. So this is our second guess. Call that x2. Now we can repeat as desired. So we can do this, we can find x3, x4, x5. Let's go ahead and maybe draw one more of these things. So if I draw another tangent line, there we are, and we can figure out where it crosses right here, and that would be maybe my third guess, right? And then we can go up here, that's my x3, and we could do another tangent line and another tangent line. So again, we're drawing tangent lines, figuring out where they cross, and that becomes our next guess. And that's why it's kind of algorithmic, right? Because you can run this for, 100 steps or 1,000 steps, things like this. You can get better and better guesses. All right, so let's go ahead and figure out, right, if I wanted to write down some equations or something to actually, what's a fast way to remember this? Well, let's go ahead and do that on the next page, right? So let's see algebraically what this method becomes. So again, the first step is that we start off with some x value, some initial guess. The second thing that we did was that we found the tangent line. Okay, so I know an equation for the tangent line. It's going to be y minus f of x1 is equal to f prime of x1 times x minus x1. Okay, so there's my tangent line. The third thing we did is that we figured out where does this tangent line cross the x-axis, right? When does it have height 0, or when does y equal 0? So I can go ahead and plug in y equals 0, and I want to know for what x value does this occur. So I'm going to go ahead and try to solve this for x. Okay, so if I'm trying to solve this for x, maybe the first thing that I do, let's go ahead and divide through by this derivative here. And so if I divide through by this derivative, I'm going to have negative f of x1 divided by f prime of x1. And then we have on the right-hand side left over x minus x1. Let's go ahead again, we're solving for x. So let's go ahead and move over this x1 minus f of x1 divided by f prime of x1. So that x value, where the y was equal to 0, where that tangent line crossed the x-axis, that becomes our second guess. So I'm going to go ahead and label this x2. That's my second guess. And then we could figure out, same thing, what is the tangent line for the function at this point, right? So we would have y minus f of x2 is equal to f prime of x2 times x minus x2. And we could figure out when this crosses the x-axis, right? Where this y value is 0. And the process just keeps on going over and over and over again. And so I want to give you a formula for this, right? Is that if you want the next guess, right? So if x1 is the initial guess, right? We're trying to find some root of f of x. Then, if you want to get the next value, right? So I'm going to do the n plus first guess. Well, this is going to be x sub n minus f of x sub n divided by f prime of x sub n. And again, this is where n is greater than or equal to 1. So again, let me go ahead and maybe plug in a value really quick and show you how this works, right? If you want n equals 1, so you're going to get x of 1 plus 1, that's 2, right? So we're going to be getting our x sub 2 formula here. Well, that's going to be x sub 1 minus f of x sub 1 divided by f prime of x sub 1, right? And that's exactly the formula that we came up with over here. X sub 1 minus f of x sub 1 over f prime of x sub 1. And the claim is, so if we wanted to do this for maybe x3, right? If I wanted to get my third guess, let me go ahead and kind of back up for a second here. So that would be when n is equal to 2. So if n is equal to 2, right, this would give me my x sub 3, my third guess. This would be x sub 2 minus f of x sub 2 divided by f prime of x sub 2. And the claim is if you were to actually solve this one up here for x, right? Let's go ahead and do that really quick. Minus f of x sub 2 divided by f prime of x sub 2. That's equal to x minus x sub 2. So we get x is equal to x sub 2 minus f of x sub 2 divided by f prime of x sub 2. That would be our third guess. Notice that this formula exactly matches what we have right here, right? Our third guess is going to be given by x sub 2 minus, and exactly it follows this. So whatever your previous guess was, this x sub n, you can use that to figure out your next guess. But again, this, I know people are kind of tempted just to memorize this formula right here. It's important to realize what this is doing. And that's kind of why I start with this graph and this picture, right? Of trying to figure out what is Newton's method actually doing. If you just kind of memorize this, it kind of loses something, you know? All right, let's see if we can apply this to a particular example. So approximate the root for the function f of x equals x to the 6th plus 3x plus 2, and it's already specifying for us our initial guess. x1 is equal to 0. So let's go ahead and use this and see if we can calculate out x2 and x3. It's noting here that we do not have to simplify. Okay, so using this formula above, let's go ahead and calculate x2, which is equal to x1 minus f of x1 divided by f prime of x1, right? So everywhere we see an n, I'm plugging in 1, and that gives me x of 1 plus 1, that's x2, right? That's our second guess. Well, in this case, x sub 1, it's specified for us, it's 0. So we have 0 minus f of 0 divided by f prime of 0. Now these things we can calculate out. So if I wanted f of 0, well, I'll just plug in 0 everywhere I see an x, and that's going to give me 2, right? Because 0 to the 6th plus 3 times 0 plus 2, that's 2. F prime of 0, well, let's calculate out f prime of x first. 6x to the 5th plus 3, and now f prime of 0. So f prime of 0, again, plugging in 0 everywhere we see an x, we just get 3. So this gives us that our second guess should be 0 minus, so that's just going to be negative, f of 0, which is 2, divided by f prime of 0, which is 3. So again, our second guess is negative 2/3. So there is one of our answers, right? We want x2 and x3. So there is our x2. Okay, if I want x3, our third guess, right? We're going to take x2 now, subtract away f of x sub 2 divided by f prime of x sub 2. Again, we already know x2 is negative 2/3. So negative 2/3, we're going to subtract away f of negative 2/3 and divide that by f prime of negative 2/3. Okay, let's go ahead and plug these things in, and this is the important bit where it says, right, you do not have to simplify. So if this came up on web work or quizzes or exams, right, you do not have to simplify this. So negative 2/3 minus f of negative 2/3. So let's go ahead, I'm going to put a long division bar there. So f of negative 2/3, so this is going to be negative 2/3 to the 6th, right? Plus, okay, let's see, 3 times negative 2/3. 3 times negative 2/3 plus 2. So actually there is a little bit of nice simplification that we could do if we wanted to, but we don't have to. All right, so that is my f of negative 2/3. How about f prime of negative 2/3? Well, here's my f prime of x. Let's go ahead and plug in negative 2/3 everywhere we see an x. So we have 6 times negative 2/3 raised to the 5th power plus 3. And that right there is my third guess. And I don't know about you, but I want to visualize this. So let's go ahead back to our Desmos here, and let's go ahead and change this. So I'm going to have x to the 6th, and I'm going to go ahead and put, 3x here, and plus 2 here. And let's go ahead and zoom out. It looks like we want our initial guess not to be at 1, but at 0. And let's go ahead and take off a few of these things, and we'll build them back up here. Okay, so here is our picture, and we have the tangent line at 0, and it crosses down here at, yes, negative 2/3, right? Negative 0.667, and that creates our second guess, right? So that is our x sub 2, and now we can use that to create yet another tangent line, right? So here's another tangent line, and where it crosses, that is our x sub 3. So even though it looked very messy and horrible, right, it's right around negative 0.7064. Okay, fair enough, right? So that's what this horrible answer over here is. It's around that negative 0.7-ish. And you can see it actually does a fairly good job. If we had calculators or computers, right, we could do this more and more and more. We could run it and have it do 100 guesses or 1,000 guesses sort of deal. You can also notice that in this case, right, there are two roots going on here, and it of course only finds one of these things. And so our next video is going to be talking about some of the technicalities behind Newton's method, right? Anytime you have an algorithm, you wonder, when does the algorithm converge? When does it actually find the thing that you want it to find? That'll be our next video. I'll see you guys then.